The name of this video is Ferromagnetic Materials. As promised in the previous video about the classification of magnetic materials, the one which we didn't study in that video was the case of a non-linear magnetic material, which, as it turns out, is actually one of the most important type of magnetic materials. For example, examples of magnetic materials are iron, nickel, cobalt, or magnetite, which again is the material utilized to make your magnet that you put on a fridge. So it's iron oxide. Okay, actually it's 3, 4. Also, many rare earths are actually can be used as strong ferromagnetic materials. Now, what we intend to describe qualitatively in this video is the functional dependence between the magnitude of B by means of a function which we just call B itself, for simplicity, of H. So B of H means it's a generic function of H, and we want to study empirically this function. As it turns out, for ferromagnetic materials which are nonlinear, this function happens to be, of course, nonlinear, multi-valued, but also, so it's not anymore B equal mu constant times H as we have seen before, is multi-valued, which is an interesting feature. And as a sub-case of being multi-valued, it presents a hysteresis. Okay, so empirically, that is, by means of experiments, we can plot this function which looks as follows. So as before, let's plot here B. Our knob, as always, is H. On the x-axis, this is the origin with 0 H, which means 0 caret IC. Remember, the H is actually due to IC. So in this case, if we were to plot this function, we would find something like this. Let me exaggerate some of the features to make it look a little bit more clear. Actually, let's redo it a little bit better. So the first part is okay. Down here, I want to leave a little bit more space. Just to be more pedagogical. So let's redo it down here. So if we start it somewhere here, I want to leave it like this. Perfect. Of course, this is just a cartoonish kind of representation of what it will look like in real life. And now I'm stressing a few points here with these dots. So we have a few points, 1, 2, 3, 4, 5, and 6 special points where this curve intersects the various axes. And so let's give names to these points. So these points are A, so we start from A. From A, we go, instead of calling it B, let's call it C, not to confuse it with this B here. Meanwhile, also, let me sketch a few other lines here, not to forget them. Perfect. So you have these points here and this point. So this point we call it C. Again, not to confuse it with B, so I skip B. D is this point here. E is this point here. F is this point here. And G is this point down here. Back to A, so we go in this direction. And we come back in this direction. This is a typical hysteresis. Okay, so now let us also call this point here as plus H max, the maximum value that over this hysteretic curve H can take, and this one is minus H max. It's exactly the opposite. Suppose that they're more or less equal and opposite. Doesn't have to be, but typically that's what we get. And here we get minus B max, which of course you can call B minus if you want, B minimum, and this one is plus B max, is plus H max. Perfect. Okay. So now what is interesting is that at these two specific points, D and G, so at this point and at this point here, D and G, we have a phenomenon called permanent magnetization. In fact, there is a B field even in absence of an H field, which again corresponds to an absence of a current IC. So there is a permanent magnetization at this point, which again means even if I C is equal to 0, yet, and remember again that this is proportional to IC, which is our knob, yet B, both at D is different than 0, and at G is different than 0. So a material with this kind of curve, clearly, is like your magnet on your fridge. For the magnet on your fridge, you don't need to apply an external current to magnetize it. It's magnetized even in absence of any current. So that's the beautiful feature of this hysteretic curve here. Now, this is a pretty complicated curve, so let's resketch one branch of it somewhere here. And here what I'm about to study is the concept of linearization, which is critical in many applications in real life. So if this is our B versus H, let's only consider one part of this, one branch of this hysteretic curve, let's say this one down here. So I'm considering this part here. But again, at these points, we know that they are G and F in this specific case. Let me just say that this one is G, this is F. And now what we want to do, we want to linearize. For example, if we were to operate somewhere in the vicinity of a point capital P, if we want to linearize, that is, if we are okay to work within a reasonable distance from this point, well, then we can linearize this highly nonlinear curve by computing the first derivative. And so this coefficient, the first derivative associated with this curve at this point, capital P, eventually we call it mu in the vicinity of capital P, so the permeability, linearized permeability of this material in proximity of point capital P, which is given by the derivative with respect to H of B computed around this point, at this point capital P. So, and this is what we call mu linear around point capital P. Okay. By means of this approximation, which is a linearization, any complicated nonlinear material in the vicinity of certain points, you can linearize it and treat it as if it were a paramagnetic or diamagnetic material, depending on the value that you get for this derivative, larger or less than mu naught. So this is a very powerful procedure to linearize a material, to make it easier to work with. Of course, if you start to deviate too far from P, then you start to explore the nonlinearity, and so the deviation becomes larger and larger. The further you go, the bigger is the deviation from the tangent. So eventually you need to relinearize it around another point, or you need to take into account for higher order terms, which make the whole thing nonlinear and much more complicated to deal with. Now, to conclude this video, which is basically the conclusion about classification of magnetic materials, it is worth investigating the relationship between B and M or M and B. So we know that B is equal mu H. So this could be, if mu is constant, either diamagnetic or paramagnetic materials, or vacuum, of course, or a linearized ferromagnetic material, ferromagnetic. Okay, so, but we are considering this linear relationship. It's useful also for exercises to solve problems. So this means that we can rewrite it as mu times the definition of H, which is B, you've seen it in the previous video, 2 videos ago, B divided by mu naught minus M, definition of the auxiliary free magnetic field. As a consequence, we can readily obtain M as a function of B. So we have the constitutive relation B as a function of H, now we want M as a function of B if you want. And so if you want to obtain it, it's very simple, we need to invert this. And so we divide everything by mu. So we have that minus M is B over mu minus B over mu naught, so I invert the signs, and I can factor out 1 over mu naught, which when I bring on the other side is negative but becomes positive with this minus here, minus 1 over mu times B. Okay, very important relationship. Valid for linear or linearized magnetic materials, so either diamagnetic or paramagnetic materials, or a linearized ferromagnetic material. The summarize this video, ferromagnetic materials, this could be iron, nickel, magnetite, like iron oxide, etc. We want to find empirically the relationship between B and H. So as it turns out, this is nonlinear, multivariate, and hysteretic. Empirically, it looks something like this, okay? It can be more or less symmetric. It depends on the particular material you're considering. So as always, here we have on the x-axis our knob, which is the current IC, corresponding to H, and on the y-axis B, which we measure with the flux meter. So we have this multivariate function, which is also hysteretic, so that this is also has a memory, okay? So it depends in the way you go around it, and so it has a memory, so that's why it's also called a memory system, if you want, system in memory. So in this case, as it turns out, there are 2 points for which, even in absence of any current, there is a permanent magnetization, and that's why you can have a magnet, which even without an external current, still you can put in your fridge. Okay, and this happens at these 2 points where H again is 0, because it means IC, look at the previous video with the toroidal solenoid, IC was equal to 0. And so obviously here I meant that this is also different than 0. Linearization, so now for example, if I take this branch down here, and I want to operate around the point capital P only in the vicinity of that point, then I can linearize it by defining a mu linear at P, defined as the derivative with respect to H of B at P. So since we define it, actually, it's sufficient to call it like this. Okay, so of course, if you deviate too far away from capital P, of course, you need to retain either higher orders if you do a Taylor series, or you need to linearize yourself around a new point. But anyway, for linear or linearized materials, we can write B equal mu H, which allows us, by the definition of H, to find M as a function of B, which is 1 over mu naught minus 1 over mu B. That's it.